Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 47 and the final lecture of induction motors chapter. From the next lecture onwards, either we will start with single phase motors or we will start with synchronous motors. We will decide that. Okay. So for today's lecture, we will be learning about braking, generating, different braking and generating modes of induction motor, and also we will be learning about space and time harmonics. What are the harmonics present in induction motor? Okay, and also what is cogging, crawling, all these things. Okay, so first of all we will discuss about uh, braking and uh, generating modes of induction motor. What do we do in braking? Okay, that is what we want to know. Okay, so uh, let's get an overview what happens in induction motor. Okay, let me give you a overview what happens. So what do I know? I have this simple, I provide a supply in the stator side, okay, three phase balance supply, and the windings are also space displaced by 120 degrees. The windings are space displaced by 120 degrees. If they are space displaced by 120 degrees, and if I am applying a three phase balanced supply, then it will generate a rotating magnetic field. So rotating magnetic field will be generated. Okay, rotating magnetic field will be generated. Now due to the rotating magnetic field, that rotating magnetic field will cut the rotor conductors, because initially the rotor is stationary. Then the rotor will start rotating because due to Lenz's law, it will try to oppose the change. Initially what was the flux cut? Zero. So it will try to keep the same flux cut zero. So it will follow the rotating magnetic field that is rotating, right? So the rotor also will try to rotate in the same direction as the rotating magnetic field. So then the rotor will simply rotate, and at a steady state what will happen, where the torque, right, the developed torque and the load torque will coincide. That will be a stable point. At that point the speed will be fixed and the rotor will rotate with the same that speed only. It will be somewhat lower than the synchronous speed, because what do you know, the rotor magnetic field is rotating at some speed, what, ns minus nr, with respect to the rotor, so that the relative speed between the rotor magnetic field and the stator magnetic field is zero. So relative speed between the rotor magnetic field and the stator magnetic field is zero, right? But there is some speed difference between the rotor and the rotor stator magnetic field. Okay, so all this we have discussed already, so I'm just going through it quickly so that we can understand the concept of braking even better. So this was the overview. So ns is the stator speed of the stator magnetic field, nr is the rotor speed, ns minus nr is the speed of the rotor magnetic field with respect to rotor, because with respect to stator, what is the field? Ns. Already we have been discussing, already in the first lecture only we have already discussed this, right? So this is the thing, this is the criteria. Now what you want to do, you want to stop the motor, you want to brake. So you are riding a bike, right, and you want to press the brake. So motor is running now with speed 2500 rpm, and you want to suddenly go to zero. Will your bike suddenly go to zero? If it suddenly goes to zero, what will happen? Accident, right? Accident will happen. So it's not like you are driving the bike and suddenly you press the brake and nothing will happen. No, like you will get out of the bike, right? So like due to inertia. So of course we want to brake it, but we want to brake it slowly. Okay, so mainly there are three kinds of braking. One is the first one is the dynamic braking, that we will be discussing now, and next we will be discussing plugging, and the last one will be regenerative braking. So it is similar to DC machine in the naming sense, but the working might be different. For dynamic it is way different than what you know in DC machines. So for those who have already studied DC machines, nothing is similar. Okay, dynamic braking here, right, many things are different, like few things are similar but many things are different. Okay, so what I can comment is, here what happens in dynamic braking. In dynamic braking, what we do, we take out the supply. So before that, let me first do the marking so that you can understand a basic thing. One more thing I want to explain. Do I have the marking here? No. So dynamic or rheostatic braking is also, sometimes it is called as rheostatic braking. Rheostatic static braking, because we connect the resistors as well. So here, right, one thing we want to discuss is, let's assume that initially, like, I have the coils. These are my coils, right, in the space. So this is dot, this is dot, this is dot. Okay, and current is entering like this, IA. Let me assume this as IB and this as IC. Okay, so the current entering the positive terminal, positive uh, point of the coil will be basically the, what do you call, will basically be the uh, let me assume current entering the positive dot is as cross, or let me assume it as dot, and current exiting the dot is known as cross. Okay, so in the first case, if I notice at this point here, IA is positive. This is my IA, right? This is my current of phase A. So IA is positive, so I will assume it to be dot. It is dot. Now if I notice in the same point, my IC and my IB both are negative. I don't currently I'm not discussing about the magnitude. I'm just telling you that here at this point my IA is positive, and at the same point, same omega t, my IB and IC are negative. IC are negative. Okay, so what will happen to B? B will be cross, because current entering the dot is assumed to be dot, then current exiting will be cross. So B will be cross over here. Same for C. C also will be cross. Right, now of course this point is basically B, and this point will be B dash, this point will be A, this point will be A dash, this one will be C, this one will be C dash. Okay, so now what will happen is that yeah, so the other points will be basically dot. If one is cross, other points will be dot. So B dash, C dash will be dot, and A dash here will be cross, right? So what do I notice here is, I notice that in the top side it is generating a pole like this. Overall is what, right? Overall in the top side the current is going inwards, sorry, coming outwards, dot, right? And in the bottom side it is going inwards. So current here is going inwards, from here it is coming outwards. So basically if I curl my fingers, it will be going inwards here and coming outwards. So like, what is the magnetic field basically? So overall the axis of the magnetic field is here. Magnetic field magnetic field is going in this direction. So here a north pole will be generated, and here a south pole will be generated. Here a south pole will be generated. Okay, now you might have a doubt, sir, you just said it is a rotating magnetic field. Yes, it is a rotating magnetic field only. I do agree, it is a rotating magnetic field only. But at this instant, what is the, like, where does the poles lie? That is what I want to know. So I can see that if I curl my fingers along the direction of the currents, I see overall magnetic field should always go from north to south. That is, it is going in this direction. It is going in this direction. So north to south. So basically what I can say is, I can say that my north pole will be here, south pole will be here. Okay, north pole will be here, south pole will be here. That's it. Okay, so yeah, that was the case over here. Now I hope you understood how to identify the poles. Okay, very important concept that will be used in dynamic braking. So in dynamic braking or rheostatic braking also it is called, what we will do is, the AC supply, whatever supply we are giving in the stator side, is replaced with supply, with a DC supply in the stator, with DC supply in stator. So instead of providing a AC supply, I will provide a DC supply. So you will say, sir, what will happen if I provide a DC supply? I will just explain, because remember, what is the main purpose? Purpose is the rotating magnetic field currently is able to develop a torque here, and load torque is in the opposite direction, TL, right? And both of them equilibrium. So basically I know both of them will reach a stable point. This is my torque speed graph. if you remember, this was my torque speed graph, right? So this was my load torque line. So of course the developed torque and load torque will be both in opposite direction. So at this point both of them will be stabilized, correct? But what I want to do through electric means is that I want to develop a torque in the opposite direction so that it comes to rest, because rotor is rotating in the clockwise direction. How will I stop the rotor? How will I stop the rotor? Simply just deaccelerating it, right? Simply just deaccelerating it. How will I deaccelerate? I have to provide a torque in the opposite direction, right? Provide a negative torque. So somehow I have to think of something, right? So this is one of the way. What we do is we provide we replace the AC supply with a DC supply. So basically in the stator side I will not connect any AC supply anymore. In the stator side DC supply will be connected. So you will ask, sir, what will happen if DC supply is connected? What will happen? So if DC supply is connected, there can be two kinds of connections. Let me first take one kind of connection, then I will discuss about the other one. Okay, so this is dot 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 and I am connecting a DC supply. Okay, it's just a VDC. Okay, and for now what I am doing is I am just connecting these two windings. I am just keeping the third winding to be open. Okay, that is what I am doing. Okay, this is my A, this is my B, or let me connect the B and C, otherwise it will be a bit confusing. I will not connect the C. I will keep the C open and I will connect the B. Okay. Right. So now can you tell me the direction of current? So of course coil hoop will have some its resistance and we will add a resistance also. That's why it is called rheostatic. Let's not think about that for now. Let me tell you that what will be the current. Current will be a DC current, right? So current will be coming out of the positive terminal because supply will supply, right, power. So IDC, it will come into the dot for the coil A and it will come out of the dot for the coil B. Then it will return to the negative terminal, right? So now can you tell me what will be the direction of the poles? Very interesting. And will I first of all will I generate a pole? So you can answer in the comments below. First question, will poles be generated? That is the first question. And second question is, will those poles generate rotating magnetic field? So think about it and let me know in the comments. Pause the video and think about it and let me know in the comments. Okay, now I will solve. So just hold on. Why is this coming? Let me copy this thing, right? Let me copy this thing. First of all, pole will be created. That is for sure, pole will be created. But what will be the direction of the pole? For that, we have to first of all mark the dots and the cross in the coils. Okay. Mark the dots and the cross in the coils. So if I observe that for the A coil, like current is constant now. Like DC can also produce a magnetic field. That much you're sure, right? DC can produce a magnetic field. If I have a wire here and if it is carrying a constant current I, still it will provide what will be the like MMF, Ni, right? And Ni by reluctance will give me what? Will give me, sorry, Ni by L, right? Length will give me what? It will give me the magnetic field intensity, correct? And if I want to find out the what do you call flux, I know MMF upon reluctance will give me the flux. So all this we know, correct? So it will still, DC will still generate a magnetic field. It's not like it will not generate a magnetic field. Magnetic field will be generated. But if I notice here that now the current direction are not changing, so it will definitely not generate a rotating magnetic field. Why? Previously I was providing three-phase supply, due to which the currents were always changing, and due to that a rotating magnetic field was getting produced. But here current is constant, so whatever field it will produce, it will always remain constant, it will not change. So it will not generate a rotating magnetic field, it will generate a fixed pole. So it will be like, it will behave like a electromagnet, permanent magnet. What happens in a permanent magnet? In a permanent magnet, just like the field uh, winding of a DC machine, it will not change, right? Field winding of DC machine, it will not change. So yeah, that's why this will also not change. I mean, here also we are providing a constant DC current, it will also not change. Okay. So if I see that it is entering the dot, so again assumption is, if it enters the dot, I will assume it to be dot. Okay. And for the A dash, it will be cross. So A is here, A dash will be here, B dash will be here, C dash will be here, C will be here, B will be here. So for A dash, it will be cross. For B, if I see, it is exiting the dot. Exiting means it will be cross. It will be cross. And for B dash, it will be dot. For the other one, of course, if it's exiting a dot from one end, it will be dot on the other end. So if I observe, now the magnetic field is like, it is incoming in this region and it is outgoing. So if I curl my fingers, the axis of the magnetic field will be somewhat like this, right, along the C dash. So again, if I curl my fingers, you just curl your right hand, you will understand. So this will be north pole, this will be south pole. This will be north pole, this will be south pole. Okay. So now it is fixed, it is constant now. And remember, I had just switched the supply, so rotor is still rotating with NR speed. Rotor is still rotating with NR speed, but my field, which was generating a rotating magnetic field, which was rotating with a speed ns, suddenly has now stopped. That field has suddenly stopped and it provides a constant field. So what will happen? Rotor is still rotating with NR speed, so there is huge relative speed between rotor magnetic field, or between the rotor and the stator magnetic field. In which direction is the relative speed? If I see NR is rotating and stator is telling it what? Stator is telling it to stop, because what happens? What used to happen? I just told you, right? What used to happen? That the rotor magnetic field follows the stator magnetic field. The rotor always follows the stator magnetic field. Here same thing will happen. The rotor will follow the rotor will follow the stator magnetic field, that is, it will try to become stationary. Okay, it will try to become stationary. Okay, so yeah, that is what will happen over here. Now the point is, uh, or how intuitively you can understand, intuitively you can understand that rotor is still rotating. So this, right, this is still rotating and my field is constant, so there is some constant, always some flux cut, right? Flux cut is there. Flux cut has now increased. Previously my field was also rotating, my rotor was also rotating. Field is rotating, my rotor is also rotating, so the flux cut was lesser. Now field is constant but rotor is rotating, so there will be huge flux cut, and that flux cut will generate a current. That current will try to oppose its motion, that current will try to stop the rotor. So now a braking torque will be developed that will try to stop the rotor, that is known as the T brake. Okay, T dynamic brake, or whatever you want to write, TD brake, or whatever you want to name it, right? You can name it. Okay, it does not matter. So that is the thing, basically that is what will happen, that is the main thing. Okay, now one doubt you might have, sir, I am applying a DC, so what will happen to the equivalent circuit? What will happen to the equivalent circuit? So one thing you have to remember, that rotor still doesn't understand whether I am providing a AC supply or DC supply. Rotor is very innocent, right? Just like you. No, not like you, like me. I am very innocent person. Okay, you are very what I can say, very smart and intelligent. I mean, चालू, बहुत चालू हुआ, ठीक है? तो क्या होगा? तो what will happen here is that where was I? Yeah, I was doing some jokes, right? Yeah. So where was I? Rotor. Yeah, rotor will feel that it is seeing a AC supply. Because why rotor will feel it is observing a AC supply? Because for the rotor, right, the flux cut is kind of alternating, right? So flux cut is kind of alternating. Here I am applying a DC field, NS is here, and rotor is rotating. So the flux cut here will be maximum for this conductor. Then when it will reach here, it will be somewhat lower. When it will reach here, somewhat lower. When it will reach here, it will be negative, right? This is positive, negative. Just like DC machines. Again, it will reach here, it will be again somewhat negative, again it will be 0 here, in this axis it will be 0, again here somewhat positive, again here maximum. So the although I am providing DC supply, rotor feels that it is observing AC. Reason explained at the top. So the equivalent circuit on the rotor side will not change actually. So equivalent circuit on the rotor side will be this, right? This is my JX2, and I'm directly drawing the rotor equivalent, okay, electrical equivalent of the load, basically including the winding resistance, R2 divided by S prime. Now remember, this time the slip will be different. Why the slip will be different? Slip will be different because remember, the slip was with respect to the stator rotating magnetic field. Now there is no NS, there is no stator rotating magnetic field. NS is 0 now, right? Stator magnetic field is not rotating, so slip, right, also will change. We will discuss about this. So this will be the equivalent circuit, and the rotor will still feel that I still have a magnetizing reactance. I'm ignoring the core resistance, air gap resistance, basically JXM. And in the stator side, actually in the stator side, the reactance will be short circuited. Why? Because in the stator side I am providing DC supply. So in the stator side the reactance will be short circuited, X1 will be 0 because DC supply, right, on the stator side. Okay, so this portion is the stator side, and this portion is the rotor side. Okay. So now what will be this S prime? That is what we want to discuss. What will be the S prime? Okay. S prime we can understand from this, right? If you remember in the first case one, what was the slip frequency? Sorry, what was the frequency of the induced EMF in this case, right? So here if I write somewhere the frequency of the induced EMF, do you remember? So I will draw here only. So frequency of induced EMF, how it is to come? It was to come FR, that is rotor frequency, was equals to SF. Why it was SF? What does SF means? Okay, so what is S? What was S in this case? It is NS minus NR divided by NS, correct? So if I replace here with S, so this will be NS minus NR, and what is F by NS? So I know NS is equals to 120 F by P. So my P is basically 120 F by NS, right? F by NS is P by 120, P by 120, which is a constant number. Or I don't want to comment because pole can change. How it will change, that also I will discuss. Okay, how it will change, that also I will discuss. So here NS minus NR. So what is NS minus NR? It is the relative speed between stator and rotor, correct? So now I want to do the same. I want to equate this equation with this equation. Okay, so from there I will be able to understand what is S prime basically, right? Because S prime will be different because the stator rotating magnetic field is not rotating, so this load, right, will feel different. Okay, so this is just a fictitious load, right? It is not like it is actual resistance. It is the equivalent mechanical load of the induction motor that is connected on the shaft, correct? It is not like I'm connecting a electrical resistor. No, it is just a fictitious load to electrically represent. Fictitious to electrically represent. Okay, so now here again this will all depend on the induced EMF E2, right? E2, what is the frequency of the induced EMF? So again I can equate the same thing. What is the same thing? The thing is my induced EMF FR will be equals to the relative speed between the stator and the rotor. Now what is the relative speed between the stator and the rotor? It is NR. I hope you understand, right? Because my poles are stationary now. Just my rotor is rotating, poles are stationary. So whatever field it is producing, that is also stationary. So the relative speed between the rotor and the stator magnetic field is NR only, because just at the instant, just after the instant, I'm talking about just after the instant, dynamic braking has been applied. After that what will happen? Speed will reduce, so NR also will reduce. That will happen, but just after the instant. Okay, so this, right, is relative speed just after applying dynamic braking. Okay, so nr into what was the number, p by, it was basically what was the number, I forgot, where did it go, yeah, p by 120, p by 120. Okay, and this will be basically, what can I say, so this will, I will equate this in our p by 120 with s dash. So according to our formula, what do we know, it should be like basically, let me write this, my fr should be s prime into f, right, according to our formula. But our f right now is not there actually, because f was supply frequency is not there. So I should not write this in terms of f, I should write this in terms of something else. So this is equals to s prime, what is f in the previous, in terms of slip, if I want to say in terms of slip, right here. So here, if I want to write this in terms of slip, so if I want to write my s in terms of slip, how will I write my s in terms of slip? So I know this formula, nr equals to 1 minus s into ns, correct? And ns is 120, nr is equals to 1 minus s into 120 f by p. So from here, if I want to write what is my f, right, in terms of s, so f in terms of s is nr into p divided by 120 divided by 1 minus s. Okay, that is equals to f, right, because f currently is 0, right, I just want to write my f in terms of s. Okay, that is my task basically, just give me 1 second. Yeah, so I will replace this, right, I will replace f over here, because f currently is 0, I want to write f in terms of slip and nr. Okay, so if I replace this, right, with f, and this, right, is equals to what, fr, we have just calculated it, it is nr into p divided by 120. So from here I can understand that my s prime, right, new slip will be 1 minus s, it will just be reversed. Does it make sense? Does it actually make sense? Kind of does. Why? What is slip actually? Slip actually tells me the lag between the stator magnetic field and rotor magnetic field, right? This is what the fundamental definition of slip. Now, when both stator magnetic field was rotating with ns and the rotor was rotating with nr, then the lag between the stator, sorry, not between the fields actually, between the stator magnetic field and the rotor basically, not the magnetic field, sorry, between the stator magnetic field and the rotor, right? So the lag was basically ns minus nr, something like that, correct? So that much amount of speed the rotor magnetic field was rotating with respect to stator to be stationary with respect to the stator rotating magnetic field. Okay, lot of confusing terms, but all these have been taught to you. Okay, but suddenly what I did is suddenly I made the ns to be 0. If ns is suddenly 0, the rotor is still rotating with nr speed, but stator is stationary, right? So the relative speed will be much higher. So because at full load, if you understand that if the ns is 1500, generally the full load speed of the rotor is 1440, something like that, right? So the lag is very small. nr is almost equals to ns at full load. Now, if suddenly this goes to 0 and still the rotor is rotating with nr speed, then what is the lag? That is what they're asking. Then what is the lag? The lag is simply nr only, right? The lag is nr only because stator is stationary. Stator is stationary, lag is nr only. Okay. What was NR? NR was equals to 1 minus S into NS. So this is the lag actually. Now 1 minus S is the lag. How can you understand? So higher the slip, higher the lag. So here, right, what was the slip? So approximately I'm just writing the values over here. Let's assume 0.05 or something. Here what will be the S prime? New slip, it will be 1 minus 0.05, that is 0.95, which is very high, which is actually correct, right? Because the relative speed here is higher, it is NR. Here what was the relative speed? It is NS minus NR. Relative speed is higher, so the frequency that will get induced in the rotor side will also be higher, that is this frequency NR into P divided by 120. It is higher, right? And now, okay, so although we write our E2 as the standstill reactance, but to convert to standstill reactance, what did you do? To convert it to standstill, that is it independent of the S term, the slip term, basically we divided by S, if you remember, and after dividing by S, this X2 became constant, this E2 became constant, but we got a fictitious load, that is R2 by S. So the load will be higher now. Does it make sense? Does load getting higher make sense? Load getting higher does make sense, because now what will happen? The basically supply will feel I am supplying more higher torque because it is providing more opposing torque. So what do I mean by it? Previously, if you see the graph here, previously the load torque was only the opposing torque. Previously the load torque was only the opposing torque. So supplied current according to this load torque. Higher the load torque, higher the stator side will supply the current. Now what happened, as we gave a DC supply, what happened is slip got changed. Slip got changed, this load got higher. If this load got higher, supply has to send in more current. If supply has to send in more current, does it make sense? Yes, because overall what will happen, this graph, right, the motor will not generate a torque anymore. It will create a opposing torque. Why it will create a opposing torque? It will create a opposing torque, and the graph and the operating point will be somewhere here, because previously this was the operating point that was at S slip, right? Now it will shift to 1 minus S instantly. It will go to 1 minus S instantly. Okay, I hope you are able to basically understand basically graph will also be flipped, right? Sorry, what do I mean? NR is same, right? So this is the speed NR. This speed is NR, right? Torque speed graph I am drawing. This is the speed. So now the motor will generate a opposing torque. Why it will generate opposing torque? Because I just have told you that here, right, it will provide a braking torque. Why? Because field has become stationary, rotor is rotating in this direction, stator is saying stop, stator is saying to stop it. So of course the current will be generated due to flux cut, such that it will oppose its cause, that is basically it will try to stop it, right? Because constantly if this rotor rotates in the clockwise direction, there will be constant flux cut, but I want to oppose that, I want to change that. So for that, what do I have to do? So for that, basically I have to slow this rotor down. If I slow this rotor down, what will happen? The speed will reduce. So basically what I am doing, how am I slowing it down? Because I want to make it stationary, because I want to make the flux cut to be zero, because the stator magnetic field is stationary, the rotor magnetic field also should be stationary. So I want to make it zero, so I have to develop a opposing torque. So that's why the torque developed will be opposing, and it will be flipped. Graph will be flipped. Why it will be flipped? Because the operating slip has changed. Previously if the operating slip was S, now it has become 1 minus S. So this 1 minus S point, whatever this one point will come here, this S point will go there. So basically the graph of the opposing torque will be mirror image but flipped. Okay, so this point will be basically the 1 minus S point, right? This will map to here. So very interesting and important point to understand. Okay, very interesting and important point to understand. So that is one important point that we have to understand. So what are the key points? The key points is basically these are the two key points that I have already written, that AC supply will be replaced with the DC supply. Motor still operates in motoring region. What do I mean by motoring region? I will just explain. Motoring region basically means the slip will lie between the range 0 to 1. Okay, with number of poles becoming fixed because I am applying a DC supply, right? And the third point will be the slip will now change. The third point, I will write here in the third point. the slip will now change S prime, S new, it will be 1 minus S old. So the graph, right, the developed graph will be somewhat like this. The torque developed will be somewhat like this, right? Okay, if I'm drawing the graph correctly, it will start, it goes to 0 here, right? Yeah, it goes to 0 here and it is some constant value. So this will be the braking torque basically. It will be opposite, that's why it is negative. With same NR speed, okay, same speed direction, the braking torque will be opposite, right? Developed torque will be opposite because it is trying to break it, stop it, right? Very important point to understand. So again, can you tell me what will be the max point of maximum braking torque? Do you remember something? Do you remember what was the condition, the slip at maximum braking torque? So basically, I have to find out the slip at maximum braking torque. So basically, I know that in normal condition, what used to happen, I used to equate S equals to R2 by X2, right? Rotor resistance upon rotor reactance. But now S has changed to S prime, slip has changed. So this will be 1 minus S will be equals to R2 X2, and at this slip, basically, at this old value of slip, I will observe the maximum braking torque. Okay. One more thing is we add resistance to increase the braking torque. How? I will explain. Before that, let me come to another point is what is the magnitude of the braking torque? How do I calculate the magnitude of the braking torque? Right. So before that, yeah, let us first say that the current that is flowing is I2 in the rotor side, right? Can you tell me what will be the magnitude of the braking torque? Very simple and easy to understand. So what will be the torque? T brake, it will simply be equals to 3 by omega S into I2 square into R2 divided by S prime. Remember the slip has changed now. Remember all this, right? Slip, it just represents the fictitious load. So I have to consider the fictitious load. I just cannot ignore it, right? It is S prime now. Okay, it makes sense as well. It makes sense as well. Okay, so yeah, I have already intuitively explained you why does 1 minus S will be present over here, correct? So like one more point, this is 1 minus S, previously it was S. So previously, let's take few numbers. Previously, let's assume that R2 is, let's say 1 ohm, right? And S2, like S, was 0.05. So previously, what was the load? Previously, my fictitious load was R2 divided by S, that is 20, correct? Now what is the fictitious load? It is R2 divided by 0.95, that is 10 basically. R2 divided by 1 minus S, that is S prime. So it will be 1 divided by 0.95. So 1.05. So the load has almost reduced. Does it make sense? Kind of does. So previously, if you remember, whatever load was connected, mechanical load TL, was opposing. It was opposing in nature, right? Now what is happening? Now TL is not opposing anymore. TL is supporting. TL is supporting. How it is supporting? How is TL supporting? So previously, if you remember, if I just copy this graph, so yeah, if you see, electromagnetic torque was in this direction, TL was negative, right? It was opposing it. So that's why I had to provide more power. Now what is happening? TL is still in this direction only, right? TL will still oppose. TL direction will not change. It is load only, right? Load. I've just connected load. TL is in this direction and the developed torque is also in this direction. So now it's like it does not have to, the stator will understand I don't need to supply that much amount of current to bring the rotor to rest, because already the load is there to bring it to rest. What do I mean by it? So this is the rotor, right? This is the rotor. So if I, like, let's assume this is a load, right, in the rotor. So if I, with this rotor, if this load is also rotating, this load will try to oppose it because it has a inertia, it has a weight, right? It will try to oppose it. If this load is not there, then by simply, if I want to stop this rotor, then it will stop. If I provide the same torque, it will stop later. Okay, I hope that makes sense. What do I mean by it is basically if your fan comes to rest without any load in 10 seconds, now if you keep a load in it, right, if you keep a box or something and then you press the off button, it will come to rest much earlier because already there is a load in it that will also help aid in bringing the motor to rest. So load will aid, so this will aid, TL will support, that is it will aid, right, the braking phenomena. So that's why the current required will be less. So this is also another intuitive understanding of this. And trust me, nowhere you go, anywhere, okay, any, like I cannot name the coachings, you go any famous coaching anywhere else, no one will even explain this topic. I'm giving you 50 minutes for this topic, okay? Everyone will just teach you 5 minutes of this topic, 5 minutes, and then they say like we are just teaching rubbish things, okay? And trust me, one day gate examiner will ask you some good question from this and you guys only will be able to solve it, okay? So that's why this is the depth, that we are going into, okay? Only you guys will know, you guys will understand this. You can see, you can compare any other coaching notes anywhere, right? They don't even teach this stuff, okay? So that is one thing. So you have to find out I2. How will you find out I2? So you will be given E2, right? Stand still, like basically what they will give you, the supply voltage, right? From the supply voltage, the drop here, you can assume it to be almost negligible. You can find it out here, okay? You can write E2 here. Now actually this E2 and supply voltage can be different. So how do I find it out? So one thing I know is, okay, this is I2, right? Yeah. What will, now remember, what will be the DC current that the stator side will provide? So electrically actually they are not connected, right? There is air gap. So sorry, I have written it opposite, right? This is the rotor side, sorry, this is the stator side. I'm sorry, I'm really sorry. This is the stator side, this is the rotor side. I'm really sorry, right? Stator side, rotor side. Okay, so yeah. So actually stator side is providing DC only, but in the rotor side I have I2 dash current. So how will I equate it? So now comes the concept of MMF balance. So whatever concept we have learned in transformers, those are still getting used here because it is just like a transformer only. So now we will discuss the calculation of stator current, stator DC current. Okay. So before that, let me discuss, if previously I had a stator, right, that was providing AC supply and AC currents were flowing through the coils, what was the MMF? What was the MMF? If you remember, the MMF came out to be 3/2 into N, whatever the number of turns, into IM, right? This we had already derived in the starting of induction motors, if you remember, right? Okay, this we already know. So this is basically the MMF balance equation. So ultimately the thing is, I am actually providing here DC current only. I am actually providing DC current only, but actually the rotor is feeling that I am providing a AC current to the stator. Rotor still doesn't know. Rotor still doesn't know that I am providing a DC current. Rotor does not understand. He is very innocent, right? Rotor is very innocent. Rotor does not understand, right? I am still providing a AC current. He feels that. So he will feel that I am sending a I1 current that is getting divided between here and here. So roughly we can, if you neglect this XM, I1 will be equals to I2. Okay, roughly if I neglect this XM, so I1 will be equals to I2. I1, so here only if I copy this circuit, right? So in this circuit lot of things are hidden here, okay? Just be careful regarding that. So what I can say is, roughly if I ignore JXM to be very high, then I can say I1 will be roughly equals to I2, which are AC currents. But actually in the stator side, I am not supplying any AC, I am supplying DC only, right? So I will fictitiously understand, because what is the task of the stator? Task of the stator is just to provide the MMF. That is the task, right? So fictitiously, if I say that if I was supplying a AC current, then this was the MMF that would have been developed. Balanced three-phase AC current, right? N into IM. Now what is IM? Basically IM is root 2. IM will be root 2 times I2. It will be actually root 2 times I1, which will be roughly equals to root 2 times I2. So here I can replace this by 3 by 2 into N into root 2 times I2. So this is the fictitious or the MMF that I needed to supply to generate a current I2 in rotor, right? Now actually I'm not providing a three-phase balance supply in the DC side, right? In the stator side. So actually what is the MMF? So there are two connections. So I have already explained you the first one. So now we will calculate. There are two connections actually. We will see one by one, right? So we'll disconnect everything, will not connect anything. Okay. So there are two options, right? There can be other as well, right? I'm not constraining it, but mainly these are the two most famous one. There can be other one as well. We will take it as a question as well. Okay. So I will give you two ways. So first one is, as I have already shown to you, that only the two phases are connected, A and B phase, right? Or other phase also you can connect, no problem with that, right? So then this will be the direction of the current. But I can connect the three phases as well, right? What I can do is, I can somewhat connect it like this. I can connect the C phase as well. So basically what I will do, I will short both the B and C phase, right? Short both of them. So then the current will not be any more IDC here, it will change. And if the current changes, then things will change. So this will be IDC by 2, because both coils will provide equal resistance. So this will be IDC divided by 2. This will be IDC. So let us compute the MMF provided by each of these. Remember, it is DC, so it will be far easier for us to calculate the MMF. Don't worry, I know you are scared, but it will be far easier for us to calculate the MMF, right? So MMF in this case, if I draw the phasor diagram in space, right, in space, so this is providing a flux. Like here current is entering the dot, here current is leaving the dot, here nothing is there. Okay, so if I draw this resultant circuit, right? So basically current, let me assume A dash to be reference. So if A dash is reference, so this will be my this will be my reference basically, uh, reference current IDC, which is entering the positive terminal of the A. So I know that B is space displaced by 120 degrees. So if there was a positive current in the B phase, it would have been placed somewhere around here, right? 120 degrees, correct? As it is space displaced by clockwise in 120 degrees. But actually, I am observing that current is leaving the dot. So it is a negative current. Negative current means it will just be in the opposite phase of the actual B phase. So the magnitude is same, IDC. So what is the angle? So this angle is 120. This whole angle is 180. So this angle will be 60. Right? This angle is 60. So if this is 60, right? So then what will be the equivalent? What will be the equivalent I resultant or MMF? So this is the MMF provided by the phase A, N into IDC. This is the MMF provided by the phase B in this direction, N into IDC. So the resultant will be N into I resultant, right? Resultant MMF. So how do I calculate the resultant MMF? So very simple, right? Vector addition of two magnitudes of same value. So it will be 30 degrees from here. Okay, 30 degrees from here, and the magnitude will be simply uh, root 3 by 2, correct? If I remember it correctly, it should be, or no, sorry, root 3, right? It should be simply, basically, you can do the vector sum, like you can do it. So n into I, like I resultant will be basically under root IDC whole square plus IDC whole square plus 2 I1 I2, that is IDC whole square again, into cos 60, basically cos 60 is half, right? So it will be simply root 3 into IDC, root 3 into IDC. So this will be my resultant current basically. Okay, let us calculate for the first one only. Okay, it will take a page, so let me take the first one actually. Take a page, not cut, not cut. Okay, so this is the resultant basically. Now I will equate this with the MMF that is required. What is the MMF required? MMF required is 3 by 2. MMF required, because rotor is filling, still I am supplying AC, will be equals to MMF provided, right? I have to equate it, then only it will work, then only the braking will work. So basically MMF required will be 3 by 2 into N into root 2 into I2. I2 RMS, remember that is RMS current. Generally if I am not mentioning anything, it is RMS only. Okay, so this will be equals to root 3 into IDC, okay, into N basically, because this is the resultant MMF that I am actually providing. So from here I can easily find out what will be the magnitude of the current that will be supplied, right? Or you can find out what will be the magnitude of I2. So I2 IDC will be equals to root 3, this will be under root 3 by 2 . under root 3 by 2 into I2. Okay, under root 3 by 2 into I2. That is what IDC will be provided. Okay, so yeah, this is the value of IDC. Okay, what about the second case? So there can be many cases here. Again, this was generating a two-pole machine. We can generate multi-pole machine as well. Okay, we will like you can make a combination. You can do it. Okay, but number of poles will be fixed. Why? Because current is fixed now. Current is not changing. Number of poles you cannot change. Like once you are like decided, you will provide it like this. So this was the first case. In the second case, something similar. I will directly do it now, not explain it. Okay, so this is my A phase, which is providing an IDC. Okay, and the B phase is here clockwise, but current is leaving, so it will be negative direction. This time the magnitude is NIDC by 2 because current is halved, and C positive direction should be somewhere here, but again current is leaving the dot, so it will be negative, that is here. NIDC divided by 2. Again the same thing, right? Again I will magnify and zoom this in. So this will be 60, this will be 60. This will be 60, this will be 60, right? So what I can say is, now what will be the equivalent? So now the equivalent, so kind of different. So this will, if you see, this is kind of symmetric, right? So it will have two components. One component will be along the y-axis and one component will be along the x, for both of these, NIDC by 2, NIDC by 2. So for both of them, the y-axis component will simply get cancelled. Only the x-axis component will be there. So NIDC by 2 into cos 60 plus NIDC by 2 into cos 60. So this is what? So 2 into n IDC by 2 into cos 60, that is provided at the x-axis, and already a component is there for the A phase plus NIDC, and remember the y phase components are getting cancelled. So this will be equals to basically 3 by 2 NIDC. So this is the MMF provided from the DC supply. Now I will equate this with the fictitious value, that is 3 by 2 n into root 2 into I2 equals to 3 by 2 n into IDC. So my IDC will simply be, in this case IDC will simply be equals to root 2 into I2. Okay, that's how simple it is. Okay, many no one will teach you this, trust me, no one will teach you this. Okay, and remember like this, right, I2 is just the fictitious I2 current that the stator needs to supply, fictitious current, AC current that stator needs to supply. Okay, so now you are well equipped to do what? To solve numericals. So we have discussed mainly three things, right? What happens in a rheostatic braking. Today we will not be able to discuss about the harmonics in transformers. Okay, tomorrow we'll have to discuss that. I mean in the next lecture, or I think this lecture has already gone wrong. So today we will do only rheostatic braking, this lecture, and in the next lecture we will cover the plugging and the regenerative braking. Those are easy, those are not that difficult, those are easy, and then we will do the harmonics. So today we will do only this, right? So let me quickly summarize what happens in a rheostatic braking. So first of all, main key points. Rotor was rotating with a speed nr, okay, but then suddenly what happened is I want to break the motor. So what I did, I like, one thing is you turn off the supply, right? You turn off the supply of your fan, your fan comes to rest. That is one way to break it. But I want to stop the fan faster. So what I did, I picked up my big brain and I replaced the AC supply with a DC supply. I provided a DC supply. So if I provide a DC supply, what happens is that in the stator, it generates a MMF and it creates a permanent magnet. Permanent magnet. Now, if it creates a permanent magnet, then still there is some relative speed. The stator field is stationary. Rotor also will try to become stationary. Rotor field always follows the stator field, right? Stator field is stationary. Rotor field also will try to become stationary much faster now. So that is a task. Who will do it? Because there is flux cut between the stator and the rotor. Flux is getting cut in the conductor, in the rotor conductors. That current will be responsible for creating a additional braking torque known as rheostatic braking torque, right? Okay. So, but remember, motor still operates in the motoring region. Motoring region basically means between 0 to 1, right? I will explain this when we will discuss about plugging and regenerative braking. What are the different regions of operation? Don't worry about this for now. Okay. But the new slip will change. Why? Because there is previously, what was slip? Slip was basically the lag between the stator magnetic field and the rotor, right? What is the speed of the stator magnetic field? 0. What is the speed of the rotor? Nr. Previously the lag was ns minus nr, now the lag is nr. So that's why the slip also will change. Slip will become 1 minus s old. Intuitively also you can understand the lag has increased. If the lag has increased, the slip also will be increased, right? Slip basically defines the lag, right? Slip defines the lag between the stator field and the rotor, right? Lag has increased, right? Previously the lag was ns minus nr, now ns is gone, ns is 0, so the lag is nr is high, right? So lag has increased, so slip also will increase. Okay, intuitively also you can understand. So we equated everything, we found out like this was the torque, braking torque basically. This was the braking torque where I have written it 3 into I2 square. So if standstill induced EMF, so it is what E2 is the standstill rotor induced EMF. So you search for this word in the question. If it is given, then you will be able to find out I2. What will be I2? I2 will be simply E2 divided by under root R2 by S dash whole square, R2 by S dash whole square plus x2 whole square. Okay, R2 dash by S dash whole square plus x2 whole square. So that is what will happen basically. So from here you can find out the I2, very easy, right? So now we got I2, but I want to understand how much will the stator supply. So stator is still supplying a DC only, but rotor is feeling that stator is supplying AC. So if rotor is feeling that stator is supplying AC, so roughly I will equate these two. Basically there will be very little drop here. Okay, so I will neglect this R1. So roughly I will say this fictitious current, this is the fictitious stator AC current. This is the fictitious stator AC current. Okay, if it is a fictitious stator AC current, then what I can say is that what will the magnetic field generated by this fictitious AC current, that is equals to this 3 by 2 root 2 N2 I2. But actually the stator side is supplying DC, right? So I will equate these two because ultimately stator has to provide the same magnetic field, MMF as the whatever the rotor is demanding, right? So that's why I equate this equation here, right? For the two cases, there can be many circuits, not only one. We will take an example, we will see there can be many circuits. Tomorrow lecture we will see. Okay, so like this we can find out the mmf provided by the stator side, and we can equate the mmf, and from there we can find out the current of the stator. So if numericals will come, numericals can only come two things. Either they will ask you the breaking torque. Now remember, if they are just asking you initial breaking torque, if this term is mentioned initial breaking torque, then your actual value of torque will be equals to T brake due to dynamic braking plus the load torque, because load torque is also providing a opposing torque, right? So that also will be included in the braking torque, right? So what is the value of load torque? It is very simple. You go back to the previous steady state, right? Previous steady state. So from the previous steady state, you know the slip, you know the current I2, right? You can simply find out what will be the previous load torque. Previous load torque will be 3 upon omega s into I2 whole square into R2 divided by S. Okay, so that is what my TL is equals to, right? Previous, from the previous values you can find out. A new braking torque you have already find out. The new braking torque, dynamic braking, is equals to 3 upon omega s into I2 whole square into R2 divided by 1 minus S. Remember, this I2 also has changed, right? Now I2 current will also be different. This will be some I2 dash, right? That we can find out from here, or like it will be some E2 value induced EMF by something will be given. Don't worry, something will be given to you. So this current are not same anymore. These currents are not same anymore. Okay, these currents are different. But if they are asking you just find out the initial braking torque or initial braking torque due to dynamic braking or rheostatic braking, if they are asking just this thing, right, then you will write simply TBR dynamic. You will not write TBR dynamic plus TL. Okay, you will not write that. Okay, so this will be the initial braking torque due to dynamic or rheostatic braking. Okay, so please be careful. If they're just asking initial braking torque, you will add these two. If they're asking due to dynamic or rheostat braking, then you will just provide the rheostat braking or dynamic. So same for plugging as well. If they're asking just for plugging, you will write the plugging one. But if they're asking just the braking torque, then you will provide the sum of these two. So these are the important points that you need to keep in mind. Okay, so now let's solve a question basically on this. Okay, let's solve a very basic question on this. Okay, so yeah, this is the question. You can, like, you have learned a lot of things, so you can pause the video and write this question out and put in the comments below what is the answer. So there are three parts to this question, so we will solve all of them one by one. So one more thing I forgot to mention, one more thing. So here, right, I mentioned the slip at which the maximum torque happens. I written it somewhere. Yeah, here, right, this. So we can actually change the slip by adding some rotor external resistance if we want to, right? So that is a facility that we can do. If it is a wound rotor machine, we can add external resistance. So what we can do, we can change the magnitude of the braking torque. So I know my slip, right? The slip at which maximum torque happens will be this R2 by X2. 1 minus S will be equals to R2 by X2. So what I can do, I can add external resistance. If I add external resistance, what will happen? This graph will shift rightwards. Simply this graph will shift rightwards. So basically, if I have three graphs, So basically this, I can connect external resistance R external 3, I can connect external resistance R external 2, and I can connect an external resistance R external 1. So basically for higher speeds, basically I can provide higher braking torque by changing the location of the maximum slip, right? So like more resistance you add, this, right, this value will increase basically. R2 will become R2 plus RXT, so the torque also will increase. Yeah, roughly I2 square will reduce, this also will reduce, but this will increase by a larger amount. Okay, so like if you want to understand this, right, so how, why is it increasing here? Okay, so if I am adding, what is my slip becoming? Slip is basically 1 minus R2 plus, so here, right, my RXT 3 is greater than RXT 2 is greater than RXT 1. Okay, so this will be R2 plus R external divided by X2. Okay, so the more R external I will provide, so the slip will reduce, correct? And like what is the direction of slip? So slip here, right, at n equals to nr equals to ns is 0, here the slip is 1. So if I move in this direction, the slip increases, but it is telling me the slip is reducing. So yes, if I move in this direction, the slip will reducing. So the more external resistance I will add, so the slip will reduce. So my maximum point of maximum torque, right, the slip at which maximum torque happens will reduce. So I will move rightwards. So that's why the graph is shifting rightwards. Okay, so I hope you have understood this basic point about the graph point at which the maximum slip will occur. Okay, so these are the key points that you need to keep in mind. So this is only possible in wound rotor induction machine, because only in those kind of machines I can add the rotor resistance. Okay, a 400 volt 50 hertz 4 pole 3 phase star connected induction motor has the following parameters. Okay, so it's R1 JX1. So previously I had neglected R1 JX1, but here we cannot because they are comparable. Okay, so I will draw the circuit. Okay, so has the following conditions. So operating is this. So let me draw the circuit in normal condition. Okay, so circuit diagram equivalent circuit diagram in normal operating condition. So basically I will have this resistance R1 and XM they have not mentioned, right, there is no XM, so I will neglect the XM. Basically I will have this JX1, then the XM is neglected, XM is not present, so I will consider it as open circuit. I will have the JX2, okay, this will be basically R2 divided by S. Okay, so what I can say over here is this is the normal working condition, right? So here I will just replace the values over here, all the values, right? So if I replace the values about my R1 is 0.5, x1 is 1.2, x2 is 1, okay, and R2 is 0.3, and remember what is the slip? Slip is 0.05, right? So it will be 20 times this, so it will be 6 ohms basically, okay. So and they're providing a 400 volt supply. Whenever the supply is given, it is with respect to the stator side, it is star connected, right? Star connected meaning, so the per phase voltage will be 400 by root 3. That is what the per phase voltage will be, okay. It is a 4 pole machine, so P is equals to 4. Calculate the initial dynamic braking torque. They are asking me what is the initial dynamic braking torque. They are not asking me initial braking torque. So I just have to find out the torque provided due to the dynamic or rheostatic braking. When DC is applied to two stator phases connected in series, producing the same air gap flux. So basically what they are telling me that what will be the, if I have changed my stator supply to DC, and what it is doing is basically it is providing a DC supply, right? So here some current IDC is incoming, here some current IDC is outgoing. So I'm providing it a DC supply plus minus VDC. So basically like same thing, right? So let me assume this as A phase, this as B phase, this as C phase. So this current will be IDC and this current will be basically IDC again. So ultimately the equivalent will be something root 3 into IDC. This we have already discussed, right? So this I know, okay. And so what is the impedance that is getting applied over here? Like what is the voltage, right? Because I want to find out the current I2, right? That is what I want to find out. I want to find out this current I2. How will I find out the current I2? So before that, let me, okay, because have they asked anything, calculate the, okay, resulting braking torque. So one thing they are also, if I see in the next portion as well, they're asking me the resulting braking torque. If they're asking me the resultant braking torque, let me calculate the load torque because I would require it, right? Let me first solve this circuit. So if I solve this circuit, first of all, I have to find out the I2, right? I2 will be same as I1 only. I2 will be roughly same as I1 only, right? Because here no current is flowing through the, what do you say, magnetizing reactance, right? So what will be the I2 in this case? Okay, what will be the I2 in this case? So if I want to find out the I2 here, very simple, right? Because I want to find out the load torque, how much load is provided, right? So load torque, if I want to calculate, because for second question I will need it, so I am calculating it now only. So TL is equals to the developed torque initially, omega s, before braking, into I2 square into R2 by S, right? So I know S, I know R2, I don't know I2, omega s I know. So what is I2? I2 will be simply this voltage, right, divided by this whole impedance, right? So it will be 400 divided by root 3. So this will be 0.5, 1.5, 6.5 whole square plus 2.2 whole square whole under root. Okay, so if I calculate this value real quick, just hold on 1 second, huh? what happened here? If I calculate these values, 6.5 whole square plus 2.2 whole square whole under root into 400 divided by root 3. So it is coming to be around 33.65 amperes. Okay, that is what the current is coming around. Am I correct here? Yes, kind of, yes. Yeah, 33.65 amperes. So what will be the torque developed? What will be the torque developed? If I calculate the torque developed, this will be basically 3 by omega s. Omega s will be 2 pi into, what was the value here, 2 pi f into p by 2 or something, right? 4 pi, basically it was 4 pi f divided by p or something. This value was there, right, if I remember. So this is 33.65 whole square into r2. R2 by s is 6, right? So f is 50 only. So this will be number of poles is how much? Number of poles is 4 pole machine, right? It's a 4 pole machine. So 4 will get cancelled. So this will be 3 by pi into 50 basically. So 3 divided by 50 into pi into 33.65 whole square into 6. So it comes out to be around 129.754 Newton meter. So this is the load torque or initial developed torque, right? Electromagnetic developed torque or the load torque, because this was a stable point, right? But now this is not important. Now the circuit has changed, right? Now I am providing these things, right? Okay, and they are asking me, actually I don't need to find out the IDC. They are asking me calculate the initial dynamic braking torque. So if they are asking me to calculate the initial dynamic braking torque, now what will happen to the circuit? So the circuit, right, after applying a dynamic braking, what will happen? I am applying a DC to the stator side. So this will become short circuit basically in the stator side. This will be short circuit. So I will convert this circuit. I will write it over here. This will be S prime. Okay. This will be short circuit. Okay, this x2 will be still there because rotor still feels that I'm getting a what do you call AC supply, right? Rotor still feels that. So this, right, is still a fictitious value. Have they provided how much? Okay, calculate the initial dynamic braking torque for producing the same air gap flux. So I'm producing the same air gap flux, right? So actually we will need it because I have to find out this I2 current. I will not be able to find out this I2 current, right? Because I don't know this voltage. So how will I find out this I2 current? So they have told me that it should produce the same air gap flux as previously. So previously what was the air gap flux or MMF? That flux means same as MMF, right? So what is flux? Flux is basically MMF upon reductance. Reductance is not changing. So flux is directly proportional to MMF. Correct? So previously what was, when AC was there, previously what was the MMF? 3 by 2 into N into root 2 into I2. So what was I2? I2 was this value. So that's why we need this I2 current actually. You cannot ignore it, right? So I2 is this value. Okay. So from here I can easily find out what will be my IDC or okay, I2 is still, it has to provide the same MMF, right? If it has to provide the same MMF, okay, okay, yeah, because the torque will change. I2, so this I2 will still be remaining same. So whatever MMF that DC supply, whatever MMF previously was there, it should be same. That means the I2 current should not change. So I2 will still be equals to 33.65 only, because rotor side it is feeling like I am getting a AC current. So if I am getting a AC current, previously the AC current was the RMS value was 33.65. Now also the value should be 33.65, but actually I am providing a DC that is able to provide the same amount of MMF to produce this much amount of current. Okay, so this current will not change. If this current does not change, Load changes though. It is S prime. S prime is what? S prime is 1 minus S. 1 minus S. So basically now it will be 0.95. So R2 will be R2 by R2 is 1, so not 1, 0.3 divided by 0.95. 0.3 divided by 0.95, right? Whatever this value comes out to be. And what will be the developed torque? Now the braking torque due to dynamic braking, because they are just asking me what is the developed torque due to dynamic braking, it will be 3 by omega s. This will not change. This will be omega s only. Like basically omega s, omega r is like this, right, is almost equivalent to omega r. So that's why this does not change, because rotor is almost near the slip speed. That's why we don't change this. Okay, still it is omega s only, because you might have a doubt, sir, there is no supply frequency, how is it? So this right, we did some approximation. If you remember, here actually omega r should be coming, but here we have written omega s because omega r is roughly equals to omega s. Okay, that approximation we did. So 3 by omega s into, you can write here omega r, no problem. Okay, you will get a torque value, no problem. So let me write omega r only, because you will get confused. Because like what is power? Power is omega speed into torque, right? So torque will be what? P by omega. So rotor is rotating with omega r, you write omega r, because you might have confusion, right? So can I find out omega r? Very simple, right? So previously what was the omega r? Previously what was the slip was 0.05. So what will be my NR? NR will be 1 minus S into NS. So it is 0.95 into NS. NS is 120 F by P. Previously the frequency was 50 Hz. Number of poles were 4. So this will be 25 into this. So this will be okay. So 30 into, so 1500 into 0.95. 1500 1425 RPM. Okay, so NR is this value. So now what I can say is what is omega r? Omega r will be 2 pi NR by 60. So 1425 into 2 into pi divided by 60 equals to 149 radian per second. So here I will replace this with 149 radian per second. Okay, so 3 by omega r into new, this current will not change, just the load will change now, R2 divided by 0.95, right? So this will be 3 by 149.22 into I2 will not change because it is providing the same air gap flux, 33.65 whole square into R2 is 0.3 divided by 0.95. So roughly it will be 0.3 only. So this, right, into 3 into 33.65 whole square into 0.3 divided by 0.95, although it will be very low. Okay, am I doing it correctly? Yes, it will be actually, it will come out to be a very low value, but still it will be a considerable amount. Okay, so this will, for me it is coming out to be 7.188. this is the braking torque due to dynamic braking. Okay, the braking torque due to dynamic braking, right? So yeah, this will come out to be very low because already the load torque is providing this much amount of torque, Newton meter. Okay, so this is the answer for the first part. Okay, answer for the first part, right? It may seem like it's a very low value because remember the supply is not there, so load torque is also opposing it, so overall braking torque is something else, right? Okay, but the torque developed due to the dynamic braking is this much only. Okay, so let's now calculate for the second part. What are they asking in the second part? In the second part they are telling me that what will happen if an external resistance of 1.2 per phase is added to the rotor circuit, then what will happen? If I add external resistance of 1.2 ohm per phase to the rotor circuit, then what will happen? Then basically here, right, this resistance value will increase, then the torque developed also will increase by a lot. So this, right here, instead of this being 0.3 divided by 0.95, so this will be 0.316, right, 0.316 ohms, plus another additional resistance is connected here in the rotor circuit, that is 1.2 ohms. So now current is still same, current is not changing, just I have just added an external resistance. So now the torque developed due to the dynamic braking, right, will change. It will be 3I2 square 3 by omega r into I2 square into 0.316 plus 1.2. So this will be 0.316 plus 1.2. So this will be 3 by omega r. Omega r is this value 149.22. I2 is 33.65 whole square into this resistance 1.516. Okay, so it will become 5 times now, 5 times the torque, like the torque due to the braking, right, will increase basically. So this will become plus 1.5, sorry, this is 0.316, not 1.5, minus 0.3 into 33.65 whole square into 3 divided by 149.22. So it becomes 34.5, around 34.5. Remember, this is the braking torque due to the dynamic braking. But what are they asking actually? They are actually asking me the resulting braking torque. The resulting braking torque. So resulting braking torque will be basically, resulting braking torque will be this, right? T resultant braking torque will be the load torque plus the braking torque developed due to dynamic braking. Okay, so this will be load torque. So load torque is basically already we have computed that, that is 129.75. so this will be 129.75 plus the braking torque, that is 34.5. so plus 129.75, so this will be 164.25 Newton meter. Okay, so yeah, this will be the resultant braking torque. This will be the answer for the second part. For the third part, what they are asking, for the third part, they are basically asking me what will be the value of the DC excitation voltage required in both the cases. Okay, sorry, it should be voltage they are asking. Yeah, okay, voltage they are asking. Actually, should be DC excitation current. Voltage kind of is wrong, right? Because how will I find out how will I find out the voltage? Actually, it should be current, not voltage, because for voltage we'll need the resistance value and all those things. So voltage also you can find out, no problem with that. But actually, this should be current. DC excitation current. Slight typo. So very simple, right? What is the connection? Connection is this. Connection is this. So resultant will be 3 root 3 into IDC. So I can simply equate the MMF by DC to the MMF by AC, right? Fictitious AC. So this will be N into IDC, root 3 into N into IDC will be equals to 3 by 2 N into root 2 into the current that we had already find out, that is 33.5 33.65, right? 33.65. So your IDC NN will get cancelled. IDC will be equals to basically uh, 3 by 2 under root into 33.65. So it comes out to be 41.212 amperes of current. Okay, that is what the IDC current, IDC value comes out to be. This will be the answer basically. Okay, so very simple, not that difficult, but you have to understand like what is happening to the braking torque, how is the resistor changing, and all those things, right? So yeah, that was the answer for this question. So do we have any other question? Okay, I think one more question we had. I think we skipped that question. This is one of the question I was just finding out. No, this is only the question, right? Yeah, this is the only question. So yeah, that will be for the other one. Yeah. So with this we will end today's lecture, and we will take the same question again for plugging. Okay, so that we will discuss in the next lecture. So I hope you have enjoyed this. Trust me, this kind of content you will not get anywhere else. So make sure to hit the like button, make sure to comment down below if you feel like you have learned something new. Okay, that will really help me out, and that will be like if you appreciate us, right, it makes us even more motivated to make more content like this. I hope you enjoyed this lecture. I will see you in the next lecture. Until then, happy learning.